So, I'm going to try and keep us alive long enough to enjoy some sleep. May 2016, we had the first incidence of a lethal autonomous Tesla. And it was caused by two bad assumptions. The first assumption was that agreement between the radar system and the machine vision system would detect that the white back of a truck making a turn across the highway would be detected. And the second bad assumption was that the human in the vehicle would be paying attention and intervene. Allegedly, the person was enjoying a Harry Potter movie, and the consequences were not funny. They were dire. There are many, many other examples of flaws inherent in system design that happened long before any event. For example, 20 years earlier, the Ariane 5, at a cost of $8 billion development cycle, within 40 seconds of launch became a very expensive fireworks show. And this was because the programmers didn't afford enough memory for a large floating point number to be accommodated. The guidance system failed. There are many, many, many other examples of these problems, and these are things that we need to be aware of in design, and we need to think about them holistically from the off. And this is what I do. I think about designing cyber-physical systems of the future. But really, what does that mean? So cyber-physical systems, it's like a new buzz term for the next wave of Internet of Things or sensor networks that many people have come up with. But the reality of it is it's the integration of physical and cyber processes. And we need to figure out ways to overcome the differences between the continuous nature of physical systems and the discrete nature of the mathematics inherent in our computing systems. Effectively, what we're talking about is distributed control. Sensors monitoring our environment, actuators responding in kind, controlling the temperature, the lighting levels, the volume of my microphone. Where does this all come from? Long before we heard anything about the Internet of Things, I believe Kevin Ashton at MIT is taking credit around 1999, there was a gentleman called Mark Weiser who in 1988 joined Xerox PARC in Palo Alto. And he conceived the third wave of computing as ubiquitous computing. And what that means, what it meant to him, was that computers would recede into the background of our lives. They would become invisible. They would weave themselves into fabrics, even into our bodies. We have examples of this happening already. And we as human beings, we tend to become reliant on things, and we also begin to forget that they're there. So, for example, many of you may have had an unfortunate experience of accidentally ordering something via Alexa, or in the future, indeed, you might be upset because your smart Apple sheets aren't sufficiently well monitoring the quality of your sleep, right? So these are problems. So what comes next when we get reliant on these things? We must learn somehow to trust. And trust means that things should be safe, so no physical danger, and reliable. They should be, by and large, dependable. It's repeatable. For me, some of this stems with security. Information security. One of the underlying principles of something being, safe is that it's not open for manipulation by malicious third parties. Today we have nation states interfering with nuclear programs in other countries. Tomorrow it could be a teenager feeling a little bit mischievous with a computer. He might shut down part of our microgrid. So these things need to be taken into account by design. But oftentimes, we don't think about these things by design. They're consequential. We always say we should include security by design, but we very rarely do. We're often interested in improved efficiencies or a regulatory environment that says you must monitor this system for this so we can make an informed decision as to whether or not you're doing your job. At that point, you're looking for the cheapest viable solution to solve the problem. In any case, the formula is maximize the return on investment. That's what we want to do. And it's still fun to look at some of the figures. So I believe it's McKinsey have predicted something like 581 billion by the year 2020, which we're coming close to. And I found a figure from Accenture that says the spend on, or the added value to the economy from the industrial Internet of Things will be in excess of $13 trillion by the year 2030. These are fun figures. A more realistic figure is the 1%. The 1% of any infrastructure project that is spent on monitoring and control systems. So as we're redeveloping our water networks, as we're redeveloping our transportation networks, we are deploying these sensors and actuators and controllers. We're getting the data. But we're not often sure of how or why that will be used into the future. For example, the tube. We have a wonderful multimodal transport system in London, and we get our information through third-party apps. Google Maps, City Mapper, so on and so forth. But they get their data through APIs hosted through Microsoft Cloud Services that are fed by the data that comes from TfL, so London Underground Limited, that comes from the sensors that are used for automatic train protection systems. And these things were deployed years and years and years ago. A contract for the monitoring and control of one London Underground line, say the Central Line, back a number of years ago now, 6-year project, $6 billion, or pounds. So, or 600 million, sorry. But very expensive, takes a long time, and ultimately technologies are then used beyond their original use case, which can become quite dangerous for us. So we need to take these into account. Security is definitely one of the things that we need to look at. In thinking about autonomous systems and artificial intelligence in the future, Tegmark, in his book Life 3.0, writes that we must be able to verify, which means, did we design the right system? Validate, did we build the right system? Control, once it's out there and people are using it, can we regain some control somehow? But from our point of view, it's, can we also secure it? And this is very, very important when we think of this emerging Internet of Things. Highly distributed systems, multiple endpoints. They can be attacked from anywhere at any time. And we haven't really even thought about this yet. So we need to start thinking about it. It's something that, for me, is natural. At the beginning of my research career, I started looking at information security, so securing the bits that transfer between small devices. Doing that in a constrained way so I can have battery life that lasts for years or longer, and that ultimately the system performs as it should into the future. And then I got more into building actual applications for physical security. So in this case, we went, as part of a European project, with two objectives. We were looking at the physical security of the underground system in Rome as it was being redeveloped, and a cable-stayed bridge in Switzerland. And I'm going to talk about the bridge. In this case, we had a major problem in that a system out there needs to last and operate in line with the operational lifetime of that structure, which for civil infrastructure can be tens of years, decades, right? Two things arise. Firstly, we have an energy problem. How do we make the devices that are out there last for that long? And secondly, do we even have any examples of computing systems that exist in the wild for that long? So, fortunately, I managed to lead a follow-up project, and we went out, got access to the data, and it was really nice. We won an award for it in that we managed to, and for the eagle-eyed amongst you, you'll see the next problem here. We solved the energy problem through solar harvesting, wind harvesting. We also over-engineered it. We include some lithium-ion cells and actually a hydrogen fuel cell, just in case for redundancy. But you'll have noticed there that we came up with all these problems with reliability. The devices went offline. They were unavailable for periods of time. They didn't give us the information that we wanted. Now, this is a big problem, because ultimately it means the system's not fit for purpose. Great that we've won an award, but bad that we actually failed in our design. So, what does that get us thinking about? Well, is it the case that a remote and extreme environment is anything outside the lab for us? Which, in many cases, it can be, but in reality, when we have remote environments where there's no communications infrastructure to offload your information, where it's dangerous for human operators to exist, we conceive this idea, and this is more of a contemporary piece of work around synthetic sensor networking. So it's inspired by the concept of synthetic aperture radar, where a plane will fly over an area and map it based on the radar system and reproduce a 2 or 3D image of that environment. And we thought, well, maybe we can do this with drones for these environments. Maybe we can both collect the information from the devices and send power wirelessly to it. And of course, there's never a bad time to show a video of a drone flying around and doing some stuff. So in this case, we can see some work that I'm doing with Professor Mitchison in the Wireless Power Lab. Please do not try to do this at home. It's very dangerous, but it's lots of fun. So in this case, we can see that we can do the wireless power transfer, but again, we have lots of problems with communications that we're trying to solve. Where does this go into the future? It basically means that we have all these different problems. So if you go back to this concept of the Internet of Things, every individual thing is different, every system, every process is different, which means that every monitoring and control solution will be slightly different, very much like we're developing artificial intelligence that is very narrow. It's very good at very specific things. Double-ended answers to the same question. What's the future? We need new design processes and tools. For those of you who've seen Iron Man, an image is evoked, particularly in this hall, named after Jarvis, his assistant. So can we articulate our design requirements into a piece of software? Can it give us an answer? Can it do optimal design? And can it take into account all the very, very complicated questions inherent in the design of these systems? And can it give us an answer? Furthermore, if it's a device that we want to retrofit one of our systems with, can we automatically produce that? Can we get into the intersection of additive manufacturing with electronics, with coding? How do we do this? So these are the questions that I'm trying to answer in my research group that I co-lead, which is the Systems and Algorithms Group in Design Engineering, and more broadly with the Center for Smart Connected Futures, where I work with the Department of Computing and Electrical Engineering. And we're committed to trying to figure out this missing design science that we need to ensure the safety and security of our infrastructure in the future. And a hell of a lot of problems around security, privacy, and trust in the meantime. And this is work that will probably keep us busy for the bones of a decade. So one of the other things that I was asked to do in giving this talk was to make some predictions on a 5, 10, 20-year timeline. Now, I'm comfortable with 5 years. We'll see continuing deployments of these technologies. We'll see validation in the wild. Companies like, innovative companies like Sensat doing real-time mapping of 3D areas to inform companies like Ocado who might want to improve their efficiencies for delivery. This will happen. Technologies to improve the home will happen. Safety will improve there. Office environments will improve. Managing the safety of the air in our office environments will improve. I think air is the last uncommoditized thing we need to live. We'll get to commoditizing that soon as well. But in 5 years, I think that McKinsey estimate where we have 500 billion worth of Internet of Things devices out there, I think that's true. But what about the future? What about 2039? Do we believe that we'll have highly distributed networks, one infrastructure connected to the next? Will it be really calm? Will it allow us to relax? Will we get to the point where we can sit down in our car and rather than this futuristic vision, actually read a book, actually enjoy Harry Potter when there's no fatalities? These are the things that we're interested in solving. And these are the things that hopefully over the next 20 years we can arrive at a place where computing is calm, where it's serene, and where we can enjoy a safe future and as many good night's sleep as possible. Thank you.
David. So it looks like the crowd have spoken and there's a firm favorite, so you won't get to pick the most interesting question to start. So to kick us off, the first one, what is the one thing regarding cyber-physical systems that poses the biggest security threat?
You're going to make me pick one.
Top 3, if you like.
The biggest threat is not understanding what we're doing, what we're designing it for, and then not understanding how those people who will analyze this system might interfere with it. From a security point of view, when you've got so many potential endpoints, you have many ways to get into a system, but you've also got many new ways to manipulate it. If we consider that these systems make decisions based on information from sensors, if those sensors can be manipulated, that's a very physical act, and it's something that's very hard to detect. Oftentimes we use smoothing to take peaks out of data when we get a time series, but if we do that, and we assume that, oh, it's a flaw in the data stream, then we may have missed an event, which is a big problem. So I think that figuring out how to go about penetration testing, if we consider some of the stuff that happens today, for these new types of systems is very important. And understanding that we really, really, really need to secure these things by design, given how potentially easy it will be to interfere with their proper operation.
In line with that, it looks like we have a Cardo in the room, actually, wanting to ask about proper operation of some of the problems that you had in your drone experiments.
This is a great question. So, we thought that, first of all, we had to start hacking because, we want to get up and running. But the problems with the communications with the drone we found were we didn't really understand the nature of communications on the move between drones and devices on the ground. We had to look a lot at the electromagnetics around radiation propagation from the antenna types. Now, this stuff gets very technical very quickly. But what we found, for example, was that given those shapes, and you want to have an optimized route, in actual fact, there's no, let's say, isotropic radiator where you have uniform energy in all directions. You have to learn, in fact, it looks more like a figure 8, and then it depends on your altitude as well. And that's just to get connectivity. The speed of travel makes sense. Anything over 15 meters per second, we found everything broke. We initially started playing around with your Zigbee type protocols, and then we moved to Bluetooth because we wanted higher rate of data transfer. In actual fact, we wanted the higher rate because we got to the point where we could instantaneously transmit tens of watts, so about 60 watts of wireless power to a device instantly, which means you could charge up a bank of supercaps to last for about 3 days. But if we have an application, let's say, that's collecting audiovisual data and you've got a large file, then we need to be proximate, even with a Bluetooth connection, for 100 seconds. So we really need to figure out, how to co-optimize the energy transfer and the comms. So the next thing that we're working on there is fusing localization, because right now we need to go out and autonomously navigate based on waypoints. That only gives us meter accuracy. We need to get millimeter or kind of centimeter accuracy to turn on the power transfer to be there for as short as possible. So we want even more bandwidth. So probably Wi-Fi next, together with ultra-wideband for ranging.
Great. So we have a couple of questions that have been sitting there. The first is about London and the work that's happening in the UK. How are we versus the rest of the world in terms of IoT and cyber-physical work? Are we pioneering?
I genuinely believe we are. From working with colleagues in BT and aware of the work that's happening both in Manchester and Milton Keynes with autonomous pods, I think we're way out there. The only place we're probably not would be in the number of hours on the road of autonomous vehicles, where I think the US have the advantage. But in terms of looking at these problems and actually breaking ground and moving on, I think we're well up there, yeah.
That's great.
Yeah.
So the next question is about quantum cryptography. Can we get your opinion on this as the next security benchmark?
Yeah, so 15 minutes is a very short period of time, and I didn't get to talk too much about future-proofing devices that are deployed today. So if we get to a point where 256-bit AES is insufficiently secure because somebody has broken the particular link using a quantum computer, we need to be able to very quickly redeploy the actual information security system that we're using. That will break things from a comms point of view, because what I also didn't get to talk about was that to secure a communication requires introducing an overhead. We need more bits, which means more time, which means more computation, which means more energy, which means more memory. So these are real problems that we will need to be careful of. On the other hand, the question could be put back, do we really believe that we're going to have viable quantum computers? I don't know, maybe. I mean, it's possible. But this is something that we as a community are definitely going to have to work on.
And perhaps a good follow-up question, slightly existential, is a perfectly secure cyber-physical system possible?
I don't believe no system can be perfectly secured. Security is and always has been a game. We try to stay ahead by being smarter than the other guys. They figure out things we didn't think about. They find flaws that were inherent in the system at day zero. We try and fix them. The winner in a security competition is always going to be the one with the most resource and the best skills. So we need to make sure that we invest heavily in keeping these people on our side.
Another very nice follow-up to that, actually. Do you believe in the future we'll see international treaties to facilitate this security and maintain the integrity of our digital systems?
I think we'll need to. I think if we even look to one example of this would be logistics and crossing borders in Europe, right? So if we want to broaden that and we want to track and trace and we want provenance of components traveling from the Far East into supply chains in Europe, and we will need to actually have some trust that spans borders. Now, technical communities tend to do this quite well. It's whether or not the regulatory and governance folks can keep up with this to facilitate. I think it's going to happen.
Likely, okay. So one question related probably to what you were saying about the tube network. What percentage of today's IoT devices do you think might still be working in 5, 10, 20 years?
What percentage of today's? I would say a very small percentage. I'd say less than 10 of what we've got today. And those are the ones that will be engineered very well for a very specific purpose. They'll have gone through validation, and they'll be well maintained, even though there is a cost associated with that. But I think it'll be a small percentage.
Sorry, I was going to ask a follow-up to that question. That maybe the question is, do you think it would be secure for us to use those devices once they've been out in the world 10 or 15 years, or is it better for us to replace with new systems?
I think there will come a point where we will have natural upgrade cycles. So if you think about the underground network, that has a cyclical plan it operates on around about every 10 years or so, a line would be upgraded. At that point, the technology would be upgraded. So, you know, even with security, like the quality of security, we measure it against, you know, will this still be secure when the sun burns out? So, you know, and you can always get lucky, but as things improve, if quantum computing becomes a thing and we can easily break keys or crypto that's built into hardware, in fact, to make it efficient today, then we can upgrade that at the next cycle. I think it's more down to those people responsible for managing the networks that are controlled by these systems to ensure that.
Great. Okay, so we have one about driverless cars. How far away do you think we are from driverless cars being widespread?
Widespread. That's an interesting question. I mean, it really makes you think about, well, the technology is there. Then it's, do we have the actual infrastructure to accommodate them? So how can we upgrade the road networks with, you know, roadside units? So this is very much from the vehicular technology background. You have all these problems around dynamics with comms, with motion. So huge investment will be needed there. And then we'll need to worry about the ethics and the legality of what would happen. I mean, if we have, as I mentioned earlier, we have components coming into our supply chain to produce cars from places in the Far East, that the provenance of those components can't be tracked. So if, for example, an accident happens and you try to debug the cause, was it the sensor that failed? Was it the controller interpreting the signal from the sensor that failed? Was it the system that should have taken that together with another reading that failed? Let's say the reading was correct, and you made a decision to, actually, I'm going to kill that dog in favor of that old lady, or I'm going to kill that old lady in favor of those 3 kids. how do you go about making these ethical decisions? And there's a lot of work that needs to go into that. I'm certainly not qualified to answer that, but I think we as society need to come together and answer these questions. You know, consensus really will win the day. And that will take quite some time, I would imagine, regardless of whether or not we think the technology is capable of it today.
Yeah. I'm afraid that's all we have time for, but thank you, David.